Dave Hall was an experienced treasure hunter, spending countless hours exploring the regional park in Marlborough, Australia, in search of hidden treasures underground. It was one of his favorite pastimes, but in 2015, he stumbled upon something far more significant than he could have anticipated. While walking his usual route, Dave noticed an unusual-looking rock. Intrigued by its shape and heft, he struggled to extract it from the ground, but eventually managed to free it. The rock's surprising weight and dense structure hinted that it could be more than an ordinary find. With a practiced eye, Dave thought it might contain gold ore. However, he tempered his excitement, not wanting to get his hopes up. Once home, he tried everything to break the rock open, eager to uncover the potential gold inside. He struck it repeatedly with a hammer, but to his surprise, the surface was incredibly resilient and didn't crack. Frustrated yet intrigued, Dave realized he couldn't break it open with any tools he had on hand. Uncertain of what else to do, Dave stored the rock at home, hoping that one day he'd find a way to extract the gold he believed it contained. For the next 4 years, the rock remained untouched in his home, an unsolved mystery waiting to be unlocked. It wasn't until 2019 that Dave Hall decided to take his mysterious rock to the Melbourne Museum. He hoped the experts there could finally unlock its secrets. At the museum, Hall met with geologist Dermot Henry, whose role involves examining the samples that visitors bring in, many of which are suspected meteorites. Part of Henry's job is to verify the authenticity of these potential meteorites, a task that holds significant value in the fields of geology and astronomy. Genuine meteorites contribute to our understanding of the solar system and the intricate processes involved in star formation. Examining meteorite samples is a meticulous and precise process, and after 37 years of experience, Henry knew that authentic finds were incredibly rare. Over his extensive career, he had examined thousands of rock samples, yet only 2 had turned out to be genuine meteorites. So, when Hall walked into Henry's office and carefully pulled a large, reddish rock out of his backpack, Henry was naturally intrigued by what he saw. The unusual color, dense structure, and weight of the rock hinted that it might be something special. "This object looks unique," Hall noted, explaining how he had tried for years to break it open, suspecting it might contain gold. Curious, Henry examined the rock more closely. Goldassaing, a procedure used to test for gold content in materials, is a detailed chemical and physical analysis to identify whether a substance holds real gold or is merely fool's gold. Yet Henry sensed that this rock had a different story, and as he examined it, he began to suspect it might be a meteorite. Henry's expertise told him that the rock's unusual structure and resistance were not characteristic of ordinary earthbound stones. He prepared to conduct a series of tests to determine its origin, focusing first on identifying mineral content and metallic composition. He knew that meteorites often contain unique metals and minerals not commonly found in Earth rocks, and their surfaces sometimes display a fusion crust, a telltale sign formed during the rock's fiery descent through Earth's atmosphere. As Hall watched, Henry continued his careful analysis, his excitement growing with each test. The rock's composition, particularly its density and resistance, hinted strongly at extraterrestrial origins. Hall's simple curiosity had led him to a discovery that could hold significant scientific value. After initial testing, Henry felt more confident that Hall's rock might indeed be a rare meteorite. Further analysis would be needed to confirm it, but the possibility thrilled both men. Hall had spent years believing he might be holding something of value, and now it seemed his intuition had been right all along. This find was not just a potential treasure, it was a literal piece of the universe, offering new insights into our solar system's history and origins. Rock testing varies depending on the purpose. It can significantly expand our understanding of land composition, reveal chemical and physical profiles of rocks and minerals, and support ecological restoration of geological sites. It's also useful for creating new materials, manipulating existing ones, and aiding in technological development studies. The rock that Dave Hall brought in had a rough, carved appearance. Geologist Dermot Henry noted that this texture is common among meteorites as they are shaped by intense atmospheric heat while entering Earth's atmosphere, melting from the outside in. Could this rock indeed be a meteorite? Henry's confidence grew when he picked it up. The rock's weight was unusual, heavier than most Earth rocks of similar size, suggesting a high metal content. Meteorites generally fall into three main categories based on composition: stony meteorites, iron meteorites, and stony iron meteorites. The weight of a meteorite typically corresponds to its size, with larger meteorites weighing significantly more than smaller stones of the same type. Over time, some meteorites may also undergo weathering or erosion on Earth's surface, which can alter their appearance and even their weight. Not all meteorites are especially heavy, but certain types, particularly iron meteorites, are indeed very dense due to their high metallic content. When Henry finished the tests on Dave Hall's red rock, both men were speechless. It was confirmed to be an authentic meteorite. Even more astounding, it was estimated to be 4.6 billion years old. Henry carefully cut into the meteorite with a diamond saw, and what they saw within was beyond anything Henry had encountered in his years of work. The cross-section revealed stunning silver droplets embedded in the rock. These weren't just any droplets. They were remnants from the hot cloud of gas that had formed our solar system billions of years ago. As Henry explained, the meteorite was classified as an H5 chondrite, one of the oldest types of material known to exist. Hall soon realized that this stone's origin was far more extraordinary than any gold deposit. It carried the story of the universe's infancy, a time when countless rocks and chondritic particles circled the young sun. The meteorite was essentially a time capsule, preserving remnants from the formation of the solar system itself. The very same chondritic material once swirled in a chaotic cloud around the nascent sun, eventually merging to form Earth and the other rocky planets. By holding this meteorite, they were looking at the origins of our solar system. This ancient relic held pieces of the foundational material that would one day shape entire planets. Most of this chondritic material no longer exists in our immediate solar system, having been absorbed into planets or moons over billions of years. However, some of it remains preserved in the asteroid belt between Jupiter and Mars, where it continues to orbit, untouched since those earliest days. This discovery offered Hall more than just an interesting rock. It was a direct connection to cosmic history. This meteorite, older than Earth itself, held a piece of the process that brought life into being. Henry's analysis revealed not only the meteorite's rare composition, but also its invaluable scientific significance, connecting the ordinary act of finding a rock with the profound story of how our universe came to be. For Hall, what began as a curiosity about a heavy, red rock transformed into an unforgettable journey through time, and he left the museum with newfound appreciation. The meteorite, a survivor of billions of years, represented the incredible forces that once shaped the universe and offered a glimpse into the very building blocks of our world. Occasionally, when two celestial bodies collide, fragments are launched into space, sometimes finding their way to Earth. This is how the chondrite rock discovered by Mr. Hall began its journey. Its lack of surface weathering suggests it may have arrived on Earth less than 200 years ago, possibly within living memory, as some may have witnessed its fiery descent. In fact, residents in Marlborough reported sightings of fireballs streaking across the night sky in the 1950s. Experts are intrigued, wondering if Hall's find could be connected to an earlier event nearby. In September 1969, people in the small town of Murchison, Victoria, were captivated by a meteorite lighting up the sky with a thunderous roar. After it struck Earth, residents searched diligently for its fragments, hopeful for a glimpse of extraterrestrial debris. The Murchison community uncovered numerous charcoal gray fragments, pitted and grooved as if sculpted from clay. One peculiar aspect of the Murchison meteorite captivated both locals and scientists. The fragments emitted a strong, unusual odor reminiscent of tar, denatured alcohol, or even, as some described it, a New Jersey skunk. While some locals had to hold their noses, others found the smell faintly intriguing, describing it as wet earth. K. Ball, president of the Murchison and District Historical Society, observed how this strange scent added to the meteorite's mystery. As fragments were sent to research centers worldwide, experts eagerly began studying them. David Damer, a biomolecular engineering professor at the University of California, Santa Cruz, recalled a particularly strange encounter with the rock's aroma. When he crushed a marble-sized piece, it emitted a smoky, dusty, and sour odor. In his book, First Life, Discovering the Connections Between Stars, Cells, and How Life Began, Damer noted that the scent reminded him of a cigar butt or the contents of a vacuum cleaner bag. The Murchison meteorite remains a scientific treasure, with its otherworldly smell and cosmic origins fueling ongoing research and curiosity about the nature of life's building blocks. Recalling the rich descriptions of meteorite's scent, almost as if from a luxury perfume ad, reminds us that these extraterrestrial smells can change over time as the rocks remain on Earth's surface. The specific scent depends on environmental conditions and the volatile compounds present within the rock. When meteorites arrive on Earth, they bring a wealth of information about star formation and cosmic mysteries, offering scientists a chance to solve the puzzles of distant worlds. However, to access much of this information, researchers often have to break the rocks open. Meteorites contain isotopes that decay at predictable rates, allowing scientists to date the rock and, by extension, to estimate the age of the solar system. This dating helps researchers understand the timing of events like planet and asteroid formation. Moreover, meteorites preserve evidence of early processes such as melting, crystallization, and differentiation. Studying these processes provides clues to conditions in the young solar nebula and insights into how planets and other bodies were shaped over billions of years. In a 2020 study by scientists from the University of Chicago, the Field Museum, and other organizations, researchers analyzed premolar grains, ancient minerals from before our sun's formation. These premolar grains are exceptionally valuable because they are among the oldest known materials. To extract them, researchers ground a meteorite, creating a fine powder they placed in test tubes. The samples were then subjected to extreme conditions, alternating between liquid nitrogen and hot water baths and then being exposed to strong acids. According to Jonica Greer, a graduate student at the Field Museum and the University of Chicago, the study revealed that some premolar grains in the famous, pungent Murchison meteorite were as old as 5.5 to 7 billion years. However, something unusual happened after subjecting the meteorite to the freeze-thaw cycles. Greer recalls the scent changing to something resembling spoiled peanut butter, as if a rotten PB&J sandwich were suddenly in the lab. She attributes this shift in aroma to the release of volatile compounds trapped within the rock, a phenomenon that occurred as they ground the meteorite, exposing fresh surfaces. Over time, these gases and ices, which had remained sealed inside the meteorite, began to evaporate and disperse. Trapped gases can produce strong odors, Greer explained, and as these volatile compounds were released, the meteorite's distinct smell evolved. This discovery, however small it might seem, underscores the unique nature of meteorites. They not only hold ancient cosmic secrets but also offer sensory glimpses into the distant past. By studying their composition, age, and even their changing smells, scientists continue to deepen our understanding of the universe, from the birth of stars to the formation of planets and beyond. The piece of the Murchison meteorite kept at the Murchison and District Historical Society no longer has its infamous odor. Our sample has been exposed to the air for too long and now only has a faintly earthy scent, explains Cal, a member of the society. Interestingly, the Murchison meteorite isn't the only carbonaceous chondrite with a distinctive aroma. In 2019, another smelly chondrite crashed in Costa Rica near the town it was named after. This meteorite, often nicknamed the cosmic mud, contained organic compounds like amino acids. While some people noted that it smelled like cooked sprouts or compost, researcher Jonica Greer detected an unexpected hint of vanilla. "We anticipated a more typical scent, but it was surprisingly sweet," she says. To be clear, these scientists weren't planning on using the meteorites for a scratch and sniff test, yet their curiosity got the best of them. As Jonica herself put it, "Scientists are human too. Sometimes our noses just take over." The unusual scents of these meteorites reveal clues about the compounds within them. Carbonaceous chondrites like Murchison and the Costa Rican chondrite are rich in organic molecules that offer a glimpse into the chemistry of the early solar system. Amino acids, for instance, are fundamental building blocks for life on Earth, and their presence in meteorites suggests that some of life's essential ingredients may have come from space. Meteorites like these provide a valuable snapshot of organic chemistry beyond Earth, preserved in space for billions of years before entering our atmosphere. As meteorites break through Earth's atmosphere and hit the ground, they undergo changes that can release various compounds. The heat, combined with exposure to Earth's elements, can influence the meteorite's smell and reveal its inner composition. Each meteorite's aroma depends on its specific combination of organic compounds and how long it's been exposed to Earth's air. For example, the Murchison meteorite lost much of its pungency after prolonged exposure to air, while the recently fallen Costa Rican meteorite retained stronger, fresher aromas. Meteorites that smell like compost, vanilla, or cooked sprouts may seem amusing, but for scientists, these scents are clues pointing to complex organic structures, giving insights into the types of molecules that existed in the early solar system. Through the unusual process of sniffing out meteorites, researchers can gather unique data about the cosmic origins of organic compounds, helping us understand the potential connections between space-borne chemistry and the building blocks of life. So, while the cosmic mud might smell like a compost pile with a hint of vanilla, it represents something far more profound, a piece of the cosmos that fell to Earth, offering tantalizing evidence of the ingredients that may have sparked life itself.